De Moivre's theorem helps us to quickly evaluate a complex number raised to different integer powers, in particular when it is written in polar form. The full equation states that r cos theta plus I sin theta to the power of n equals r to the n times cos n theta plus I sin n theta, where n is some integer. But how do we know that De Moivre's theorem works? Well, we can prove it by using mathematical induction. Before we begin, let's simplify our equation a bit. Using our index laws, namely the power of a product law, we know that each factor within the brackets will be raised to the exponent outside the brackets. So the left-hand side of our equation becomes r to the n times cos theta plus I sin theta to the power of n. We can then divide both sides by r to the n. Okay, with that out of the way, we can begin proving De Moivre's theorem by induction. Let's first start with the base case, where n equals 1. Anything raised to the power of 1 is just itself. Same goes for anything multiplied by 1. So theta multiplied by 1 would still just be theta. Both sides are clearly equal, so De Moivre's theorem is true when n equals 1. That was easy enough, but what about all the other integers? We can start by proving that De Moivre's theorem is true when n equals some positive integer, which we'll call k. This will give us the equation cos theta plus I sin theta to the power of k equals cos k theta plus I sin k theta. We'll call this equation our inductive hypothesis, which we'll assume to be true. All we need to do now is prove that De Moivre's theorem is true when n equals k. It will also be true when n equals k plus 1. So we then write out another equation, cos theta plus I sin theta to the power of k plus 1 equals cos k plus 1 theta plus I sin k plus 1 theta. Let's use some algebraic manipulation to show that cos theta plus I sin theta to the power of k plus 1 really does equal cos k plus 1 theta plus I sin k plus 1 theta. We can once again use one of our index laws, in this case the product law, to show that cos theta plus I sin theta to the power of k plus 1 expands to cos theta plus I sin theta to the power of k times cos theta plus I sin theta to the power of 1. According to our inductive hypothesis, cos theta plus I sin theta to the power of k will be equal to cos k theta plus I sin k theta. And remember, anything raised to the power of 1 is just itself. We can then multiply the terms within our brackets to get this rather long expression. If you want, you can go over the algebra yourself just to verify that it is indeed correct. Okay, but how should we even begin to tidy this expression up? First of all, we know that by definition, I squared equals -1. We can then group all our real terms to the left-hand side and our imaginary terms to the right-hand side. Lastly, let's just take out the common factor of I from our imaginary terms. Okay, that's already looking a lot neater. Now what? Well, we can use our trigonometric identities. According to the cosine addition formula, cos A times cos B minus sin A times sin B equals cos A plus B. Do you see where we could apply this formula? That's right, the real part of our expression. So that part just becomes cos k theta plus theta. We can then use the sine addition formula, which states that sin A times cos B plus cos A times sin B equals sin A plus B. Again, do you see where we could apply this formula? Good job. We can apply it to the imaginary part of our expression, which becomes I times sin k theta plus theta. Finally, we can just take out the common factor of theta from k theta plus theta to get k plus 1 times theta. And would you look at that, cos theta plus I sin theta to the power of k plus 1 really is equal to cos k plus 1 theta plus I sin k plus 1 theta. We've just shown that if we assume De Moivre's theorem is true when n equals a positive integer k, then when n equals the next positive integer, k plus 1, De Moivre's theorem is still true. We already know De Moivre's theorem is true when n equals the positive integer 1. So based on our inductive reasoning, De Moivre's theorem will hold for the next positive integer, 1 plus 1, which is 2, and 2 plus 1, 3, and 4, and 5, and so on. What about the case when n equals 0? Well, anything raised to the power of 0 equals 1, while anything multiplied by 0 equals 0. So in this case, 0 times theta equals 0. The cosine of 0 is 1, while the sine of 0 is 0. So our equation becomes 1 equals 1 plus I times 0, which simplifies to 1 equals 1. Definitely true. So De Moivre's theorem is true when n equals 0. The last scenario to look at is when n equals some negative integer, say -k. Using our index laws, the negative exponent law in this case, our expression becomes 1 over cos theta plus I sin theta to the power of k. We've already proven that De Moivre's theorem is true when n equals a positive integer k. Therefore, our denominator becomes cos k theta plus I sin k theta. To simplify this fraction, we can then multiply both the top and bottom by the conjugate of the denominator. The conjugate of a complex number is just itself, except the sign of the imaginary term has been flipped, which for our denominator will be cos k theta minus I sin k theta. Anything multiplied by 1 is just itself, so our numerator is just cos k theta minus I sin k theta. That was pretty simple. As for the denominator, based on the difference of perfect squares, it becomes cos squared k theta minus I squared times sine squared k theta. Minus I squared will become positive 1. So the final expression for our denominator is cos squared k theta plus sine squared k theta. Using the Pythagorean theorem, cos squared theta plus sine squared theta equals 1 squared, meaning our denominator becomes 1, and anything divided by 1 is just itself. Okay, our expression is looking pretty similar to our desired result of cos minus k theta plus I sine minus k theta. We just need to perform a few more steps to fully convert it. First of all, the cosine function is an even function, meaning that cos x equals cos negative x. Therefore, the real part of our expression, cos k theta, equals cos minus k theta. Next, the sine function is an odd function, meaning that minus sine x equals sine minus x. As such, the imaginary part of our expression, negative I sine k theta, becomes positive I sine minus k theta. Yes, it matches with the original equation. So de Moivre's theorem is true when n equals some negative integer, negative k. We have just shown that de Moivre's theorem is true when n not just equals 1, but also all the positive integers, as well as when n equals 0 and n equals all the negative integers. Together, the positive integers, 0, and the negative integers make up the total set of all integers. In conclusion, de Moivre's theorem is true.